Hi, everyone. Our favorite vectors have what length? What's our favorite number besides 0? How about 1? 1 unit. Not even any units like feet or meters. How about 1 unit? Unit vectors have length or magnitude 1. R equals 1. We often denote unit vectors by U. Remember, if you're writing it, you want that half arrow thing. So whenever I write U, think unit vector, although not all books follow that convention. Because books might write V, W, and then they might go back to U. So be careful. When I write U, I mean unit vector, but not all books do that. Now here's something that you do all the time in Calc 3, Math 252 at Mesa. You do this all the time. You're given a vector V, you're given a vector V, all right, and you have to find the unit vector in the direction of V. This is called normalizing a vector. You're making it standard in a way. You're kind of doing a standardization process. So to do that, so first of all, what's our aim? You're given this vector, a vector V, and it may have a length like 4 or 5 meters, let's say, and you want to find the unit vector that points in the same direction. This is the vector U. And it has length, what? Length 1 unit. You can imagine a compass, okay, where the radius is 1. Your little compass here. And you see these unit vectors all the time in formulas, proofs, and derivations with vectors in Calculus 3. So how do we get from V to U? So to get from the vector V to the vector U, you take the vector V and you divide it by its length or magnitude. Now, if you're uncomfortable with the idea of dividing a vector by a number, imagine that you're multiplying by the reciprocal of that number, the reciprocal of the length. Again, normalization. We do this all the time in calculus. So, for example, find the unit vector in the direction of the vector V if V can be represented by an arrow, a directed line segment, from the initial point, 1, 2, to the terminal point, 4, 6. Here's the example I was promising earlier. 1, 2 is the initial point. 4, 6 is the terminal point. So when we draw, okay, so here's 1, 2, here's 4, 6. When we draw this, when we consider this arrow, this representation, okay, let's find the vector V in component form. What do? We basically subtract the x coordinates, new minus old, and we subtract the y coordinates, new minus old. Remember that formula way up here. Where was it? It was way, let's see, where was it? Where was it? Here we go. Okay, so you're given 2 points. Okay, find the component form of the vector corresponding to the arrow that takes you from the initial point to the terminal point. There we go. And again, it's new minus old. 4 minus 1 is 3. 6 minus 2 is 4. All right. So the vector V is 3, 4. It's a quadrant 1 vector. Okay, so we have this vector V. We have this vector V. All right. Draw it as a position vector. Okay. I want to find the unit vector that points in the same direction. Okay, first let's find the length of the vector V. The length or magnitude of V, R, right? The length of 3, 4 is the square root of 3 squared plus 4 squared. We're lucky. Here it's a nice integer. Bear in mind it could be a radical, an irrational number. We divide the vector by its length, 3, 4, all divided by 5. You do divide each component by this denominator, so we do get 3/5, 4/5. Remember, that's how we divide a vector by a scalar. Okay, we divide each component by the scalar. Okay, so these will be the components for the unit vector. And these don't have to have units. All right. We're guaranteed this has length 1. As a check, you could see that the square root of this squared plus this squared is going to be 1. This guy squared plus this guy squared is going to be 1. All right. And we love unit vectors when it comes to proofs. I'll talk more in just a moment. First off, I want you to meet our favorite unit vectors. Okay, well, the vectors that take you one step east, 1 unit east, that's called the vector I, and the vector that takes you 1 unit north, 0, 1, that's the vector j. These are called standard unit vectors. In 3 space, where the positive x-axis points out at you, here's the positive y-axis, positive z-axis. In 3 space, you talk about I, which is 1, 0, 0, j, which is 0, 1, 0, and k, which is 0, 0, 1. That's in 3 space. That's in Calc 3. Really, analytic geometry 3. Again, Math 252. This class over here. Yeah. All right. Anyway, and we often use this notation in physics. So for example, 3/5, 4/5 can be written as 3/5 I plus 4/5 j. If you don't see that, let's do this example. What if we wanted to show the deal with the vector 3i plus 4j? And I'll put my half arrowheads here. 3i plus 4j. We're supposed to distinguish between scalars and vectors, remember. All right. So what's the deal here? All right. I'll put the vector I in green. Let's put the vector I in green. The vector I, remember, okay, is the vector angle brackets 1, 0. It takes you 1 unit east. Let's start the origin. All right, so here's a vector I, okay, copy him. Here's another vector I, copy him. Here's another vector I. So here's I plus, okay, so here's, imagine these are boldface here. I'll make them boldface. I, okay, so here's I, 1, 0. Here's I, and then plus I, right? This head to this tail, I plus I plus I. So we're walking 1 unit east, and then 1 unit east, and then 1 unit east. Together, all right, I plus I is going to be 3i. How about 4j? I'll put j in, turquoise. So here's the vector j. J is the vector 0, 1. Right? So here's j. All right. Here's the vector j, 0, 1. Let's do 4 more copies. Another j. Another j. Another j. All right. So j plus j plus j plus j, that's 4 times j, all right? That's 4j. This whole thing here is going to be 4j. So what's 3i? That's like a big vector here, right? 3i is like this big vector here, all right? Plus 4j. 4j is this big vector here, right? What's 3i plus 4j? We get the resultant vector, 3i plus 4j. I'll erase these now. 3i plus 4j gets us 3i plus 4j, okay? Which is this guy here, 3i plus 4j. Or angle brackets, angle brackets, 3, 4. All right, so that's how a physicist thinks, as an addition of these sort of component vectors here, right? Physicists, I guess, like to think in terms of adding forces or displacements. Right. Okay, finally, I want to make a final comment regarding, I want to make two final comments. For one thing, in Math 254, linear algebra, here's the game you play. Let's say instead of I and J, you use as your key unit vector. In fact, they don't even have to be unit vectors. Let's say you use this vector and this vector as the basis for your coordinate grid. Okay, and I'm gonna rotate this a little bit. Yeah, let's rotate this a little bit. All right. So we get a coordinate grid that looks like this. Okay. So then we can ask questions like, all right, let's say the origin is here. All right. How do we get from this point to this point using these as grid lines? How many of these vectors plus how many of these vectors am I going to need? That's the kind of question you ask in Math 254. You're basically re-coordinatizing the plane. Another issue, where do we see these unit vectors in Calc 3, in Math 252? In directional derivatives. I'm going to explain this. What are directional derivatives? Derivatives. All right. Let's say that you look at a contour map, right? You can imagine axes here. You're looking at a contour map. And let's say that this contour, this level curve, corresponds to a height or altitude on a mountain of 3,000 feet. So this here represents 3,000 feet. Okay. And then another contour, another level curve inside here. All right. Let's say that the altitude or height that corresponds to that is 4,000 feet. And let's say that the peak of the mountain is right here. Right? There's the peak of the mountain. So here's the idea. Let's say that on your map here, you're starting at this point. Okay. Maybe the elevation is 3,500 feet here at this point on the map. Okay. On your compass, you see that you're going in this direction. Okay. What is the directional derivative of the height or altitude of the mountain if you walk in this direction on your map, if you walk northeast on your map? Right? So it's a measure of how steep the mountain is from this point that you're at, a directional derivative. And that formula involves a unit vector, the unit vector in the direction of this vector that you're interested in. Basically, the unit vector in the direction that you're interested in, right? You have a compass of radius 1, all right? Everything's standardized. So if you give me a direction, then I know what vector you're talking about. Again, it's a standardization. So we talk about directional derivatives in the direction, in certain directions, right? So the directional derivative in this direction might be positive 10 feet per meter. If by meter you mean meters along the map. In the opposite direction, the directional derivative would be negative 10 feet per meter. Okay, if again, we're talking about height or altitude being measured in meters along the mountain, and I'm sorry, height or altitude being measured in feet along the mountain, and distances along the map being measured in meters. I'm trying to distinguish between the two measures. Heights or altitudes along the mountain and meters along the map. Directional derivatives, and it involves formulas with unit vectors, which indicate direction. If you give me a unit vector, you're basically telling me a direction on your compass. What's the directional derivative in a direction? How fast, how fast is the mountain sloping up? How steep is the mountain from this point? In this way, and the steeper you climb in this direction, the harder you fall if you fall in the opposite direction. So mountain climbing and contour maps. Calc 3, Math 252.